So usually I don't do sports examples because when I was in college taking statistics, part of the reason I didn't do well was because every single example was about baseball. And I did not grow up watching baseball really at all, so I was in over my head for a lot of reasons, but partially because I didn't know what a batting average was. But this example comes from the fabulous teachers at Stats Medic. It's super good, and I just finished watching The Last Dance on Netflix, so we're going to do a basketball example today. In 2005, at the Conference USA basketball tournament, Memphis trailed Louisville by 2 points. At the buzzer, so at the end of the game, Memphis's Darius Washington attempted a three-pointer, which would have, made Memphis win. He missed, but he was fouled. And in basketball, sometimes when you're fouled, you get to make free throws. So he went to the line, he gets 3 free throws. Each free throw that he makes is worth 1 point. So the question is, was it smart of Louisville to foul? Basically, did they have a better chance of winning if he attempted the three-pointer or if he attempted 3 free throws? Like, which is the better option for them? The first thing we're going to do is outline all the possible outcomes of his 3 free throws. For example, make, miss, 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 make, miss. There's 8 different ways that his 3 free throws could go down. Just to make sure this doesn't take up, just so this doesn't take up the entire page, we'll use a check mark for make and an X for miss.
One eternity later.
Now, once we have all 8 of those outcomes mapped out, some of those are going to result in Memphis winning, some will result in Memphis losing, and some of them will result in Memphis going into overtime. So if the 2 teams tie, they go into overtime and they have to play longer. Now, we know that he is a 72% free throw shooter, and for the sake of this example, we're going to assume that 1 free throw does not affect the next. I know that in reality, if you miss the first free throw, that might affect how you do on the second one because you might be a little bit more nervous, but for this example, we'll say that it's 72% on every free throw, no matter what. We can use that fact to find the probability of each of the 8 outcomes that we list. In a moment, I'm going to have you do that. List all 8 outcomes and find the probability of each of those, and then categorize them as Memphis winning, Memphis losing, or Memphis going into overtime. Do as much of this on your own as you can, and then we'll go through it together when you're done. Pause the video now. Okay, so I have the 8 outcomes here. I'm going to start with the easiest one, which is if he makes all 3, they win. This is the only way that they can win from his free throws, because if he makes 2 of the free throws, they've only tied. So I'm going to start with the easiest one. Now to calculate the probability of that happening, it's 0.72 times 0.72 times 0.72. He makes the first one, and he makes the second one, and he makes the third one. Okay, let's deal with lose next. So of these outcomes, the team is going to lose if he misses all of them, or if he misses 2 of them. So it's these last 4 outcomes where the team will lose. So let's start with 2 misses. There's 3 different ways that he could have 2 misses. So I just wrote all of these out. He could miss, miss, make, miss, make, miss, make, miss, miss. Now, you probably saw right away that it doesn't matter the order that you multiply these, you're going to get 0.056 every time. So what you could do is just this first calculation, 0.056, and then you could multiply that by 3 to get this total probability that he has 2 misses. I just wrote it out so that you could see the different scenarios. And then, of course, there's the unfortunate outcome of 3 misses, which would just be 0.28 times 0.28 times 0.28. Now we would have to add all these together to get the overall probability of losing. We'll come back to that. These 4 outcomes represent overtime. If he makes 2 of them, he's tied the score, and now they have to keep playing to decide a winner. So 1 miss, similar to before, it could be make, make, miss, make, miss, make, miss, make, make. And hopefully you can see that it does not matter the order that we multiply those in. So we're going to get 0.145 no matter which way we multiply. So now overall, probability that Memphis wins we already had. Probability that they lose, we have to add these 4 things together. Probability of overtime, we add these 3 things together. So you can see there's a pretty low chance that they lose, pretty good chance that they're going to have to go into overtime, and an okay chance that they just win. Now, if we happen to know that he is a 40% free throw shooter, do you think that it was smart for Louisville to foul him? Pause the video, think about this on your own for a moment. Okay, so I wrote this from the Louisville perspective. If he shoots the 3-pointer, they have a 60% chance of winning. 40% chance he makes it, which means a 60% chance that they win. Pretty good odds. With the free throws, there's only a 19.1% chance that they win. It seems like they probably shouldn't have fouled him and should have just left it at the three-pointer because they were much more likely to win with the three-pointer than with him doing free throws. This scenario that we just witnessed in the basketball example is called a binomial distribution. It's a specific kind of distribution that shows up quite frequently, and so it's pretty important that we can identify it. There are 4 conditions for something to be a binomial setting, and they just happen to have a very cheesy acronym. The first condition is that our outcomes have to be binary, so there can only be 2 outcomes for each trial, basically success or fail. In our basketball example, each trial was a free throw, and success was making the free throw, failure was missing. A setting is not binomial if you have 3 or 4 or 5 outcomes. It has to be 2. Each trial also has to be independent of the others, so the first trial cannot influence the second trial. In this scenario, we kind of had to pretend that each free throw was completely isolated from the others, when in reality I know that it probably isn't, but for the sake of the example, we just kind of went with it. We also need a set number of trials. In this case, the set number of trials was 3. He had 3 free throws, he wasn't going to get more or less. It was set at 3 from the beginning. And the final condition is that you have to have the same probability of success on each trial. In our case, his probability of success was 0.72. So here's the incredible acronym, BINS. So if something is a binomial distribution, it fits the BINS acronym. B for binary, I for independent, N for number of trials, which is set, and S for same probability. Now, if you have a binomial setting, you can use a certain formula to calculate the probability of any number of successes. Let's use overtime as a way to see how we calculate success in a binomial setting. So overtime was defined as making 2 free throws, and the way we calculated the probability was a little bit cumbersome. Here it is written a little more succinctly. 3, because there were 3 different ways of making 2 baskets. And then we did 0.72 squared. 0.72 is our probability of success, and we're squaring it because we're interested in 2 successes. So I said this could be like p to the k, where k is the number of successes. And then we did 0.28, which was the probability of failure, raised to the 1. Now if we define n to be the number of trials, this is n minus k. So number of trials minus number of successes, that gives you the number of failures. In other words, probability of success raised to the number of successes times probability of failure raised to the number of failures times the number of ways that this could occur. So here's our formula written a little bit nicer. The probability that x equals k. So x is our variable. It could be number of free throws made, and k is just the number of successes we're interested in. So we were doing 2 in the overtime example. This NCK is a way that you can figure out the number of ways that you can have a certain number of successes. This is actually on the calculator. If you click on math and go over to the probability menu, it's called NCR on the calculator, and it's kind of annoying the way you have to use it. If we have 3 free throws, we'd want to type 3 first, then go to math, PRB, choose NCR, and then we were interested in making 2, so then we hit enter. There are 3 ways that that can happen. So the N is the number of trials and K is the number of successes. It's called NCR on the calculator. Then we have P raised to the K. That's the probability of success raised to the number of successes. And then we have 1 minus P, which is the probability of failure, raised to, typo, N minus K, which is the number of fails. This is like a drive-through order, like you're pulling up to McDonald's and you're ordering dinner. Yeah, I'll take 2 successes and 1 failure, please. This formula is located on the formula sheet underneath probability distribution. It says if x has a binomial distribution with parameters n and p, and then it gives you the whole formula. Couple things to note, they use lowercase x. I think that's confusing, but whatever. And they use a different representation of the NCK, where n is listed on top and k is listed on the bottom. It's the same thing, it's just written slightly differently. I tend to write it like this just because that's how it looks on the calculator. So as usual, this formula is not something to memorize, it is on the formula sheet. However, you should be able to think through it logically. I want this many successes and this many fails, and this is the number of ways that I can order those successes and fails. Okay, so why don't you pause the video and try to check your understanding problems on your own, and then we can go through them together. So for these first couple, we're just deciding if the distribution is binomial. This first one is binomial. There are two outcomes. They're either saying yes or no to this confusing survey question, do you never have time to relax? Because the survey is a simple random sample, we can assume that each person is selected independently of the others, so each answer is independent of the others. If this was like a convenience sample and they were just asking people on the street, then we might say that the trials are not independent because they might be asking like a married couple and their answers are probably going to influence each other. But it's a simple random sample, so we're fine. Number of trials is set. They're going to ask 500 adults. And the probability of success, which in this case is never having time to relax, I don't know if that's a success, but it's the same. It's 0.14 for each trial. This is the level of detail that I personally want to see on a free response question, like on a test or quiz. Your teacher might ask for something different, so just pay attention to what evidence you're supposed to show. Okay, for the second one, this one is no. We have a typo, first of all. We have all the conditions met except the number of trials. There is no set number of trials because Darcy is just logging in until she succeeds. So typically if you see the word until, that's not going to be a binomial distribution because she's doing something until she sees success. She's not saying, I'm going to log in 10 times and see how many times I get it right. This last one is also not binomial for two different reasons, and I personally, as a teacher, would accept either of these as valid answers. The more obvious one, I think, is that the probability is not the same each trial. Because we're dealing 10 cards, the probability of each card being read changes. We're not showing one card, putting it back, shuffling, showing a second card, putting it back, shuffling. We're laying out 10 cards, which means once I put down that first card, the probability of being read has changed because now I've laid down a red or a black card and there's a different number of cards in my hand. So the probability is not just 50% each time. For basically the same reason, each trial is not independent of the others. When I lay down that first card, the probability of the next card being read has changed, so those two events aren't independent. A way to make this binomial would be to show one card, put it back, shuffle it, then show a second card, put it back and shuffle it. Then the probabilities would all be the same. It'd be 50% that you get read each time, and each card would be independent of the others. Okay, for the last one, we're going back to 1A, but we're going to change n to 50. If you try to do this one with 500 in your calculator, it'll have an overflow error because the numbers are too big. So 50 Americans, find the probability that exactly 4 say they never have time to relax. I always start problems like this by writing out what I'm supposed to find. X is going to be the number of Americans that say they never have time to relax, so I am interested in X equaling 4. That's going to save you a lot of pain, a lot of confusion if you just write out what you're trying to find. Okay, so I'm starting with 50C4, which I just do on the calculator. One more review of that, you have to type 50, go to Math, PRB, NCR, 4, Enter. It's a lot of ways that you can arrange 4 successes among 50 trials. All right, now remember, this is like a drive-through order. Yeah, I'll take 4 successes, please, and 46 fails. So the probability of success raised to 4, probability of failure raised to 46. These two numbers should always add to 1, and these two numbers should always add to n. So the probability of success and fail needs to add to 1, and the number of successes and number of failures needs to add to the total number of trials. All right, so I wrote out one more step. Plug that into my calculator and I get 8.58%. If I was asked to interpret, I would say the probability that exactly 4 Americans say they never have time to relax is 8.58%. In the next video, I'll show you some shortcuts for calculating probabilities, but the shortcuts are going to be pretty useless if you don't understand what a binomial distribution is and what this formula means. So make sure that that makes sense before you go on to the next video.